Artificial intelligence methods have been shown in the past decades to be able to help in the strategic planning of a wide range of applications. From the planning of the Martian rover mission to the definition of optimal strategies to play competitive games such as Go and poker. The success of such technique in specific fields, showing abilities that are sometimes exceeding the human ones, suggests that their application to solving real-world problems may give a crucial and substantial improvement in a plethora of fields. The capability of AI technique have become evident only in the last years, thanks to the introduction of the so-called learning approach, in which the traditional AI tools have been enhanced with the capability of improving their skill of solving a problem as more information is provided. Formally, this constitutes the definition of a learning agent and in general of the machine learning fields. Citing the foundational book by Mitchell in 1997, a computer program is said to learn from experience E with respect to some class of task T, and performance measure P improves with experience E. In this definition, the focus should be given to the experience, i.e., the data coming from a specific process or setting, which is used to improve the capabilities to discriminate and decide by an automatic agent. This novel approach provides a great advantage in many different situations. For instance, when there is no human expert able to solve a specific problem, for instance in the DNA analysis. Also, when humans can perform the task but cannot explain how, for instance in the character recognition problem. Also, when the strategy to learn changes frequently, like in the predicting stock prices based on recent trading data. Also, when we need to have a customized solution for a large number of users, like in the recommendation of products. The application of such techniques in the environmental monitoring field, that we will see in this course, is about a novel approach to automatically set the parameter, for instance, sampling frequency and constraint of classical monitoring system. Let us focus on the specific task of data collection for water contaminant concentration analysis. This task involves the collection of samples and the following analysis of the water samples. Traditionally, the collection process has been performed either manually, for instance by a human operator who collects a water sample to be analyzed in a laboratory afterwards. Recently, in a wide range of settings, the manual approach has been substituted with online analyzers, which automatically collect samples at fixed frequency and use specific sensors that automatically communicate the measured value of the analyzed parameter to an external processing unit. Overall, the goal of this process is to provide accurate estimation of the measured parameter and identify those points in time and space where the measured parameter have the most extreme values. For instance, to identify the hours of the day when the concentration of a specific contaminant is maximum and therefore has a higher probability to approach or exceed the legal limit. Notice that commonly collecting and analyzing every single sample require material, for instance some chemical, and time, and therefore keeping the number of samples as small as possible provides significant saving. Choosing how often and where to sample requires facing a dilemma. On the one hand, we would like to perform the least amount of measurement to save time and chemicals, while on the other hand, we would like to have the largest number of measurements as possible to have a more accurate evaluation of water contamination. This dilemma has been known as the exploration-exploitation dilemma in the online learning field. For instance, a problem in which one wants to balance the collection of the most accurate information with the exploration of the decision to identify the best option. In our case, we want to identify the most appropriate time over the days to sample, but at the same time to select as much as possible the optimal option over time. In particular, sequential decision processes like this one has been modeled as a multi-arm bandit problem. Multi-arm bandit problems are a class of algorithms that are able to learn the best option among a finite set by relying on the feedback obtained in the past and evolving over time according to this feedback. The name of the framework comes from the original problem solved. Find the best one-arm bandit slot machine in a casino. Instead, in the framework of water monitoring, the available options are the choice of activating or refusing to activate a sampler sensor at a specific time over the day. In the last year, we worked in the development of an algorithm that was specific for the environmental monitoring setting. This algorithm builds on the classical UCB1 algorithm to extend it for the more complex sequential monitoring scenario. The simulation performed over a set of real-world sampling from a water distribution system showed that, by fixing the average number of samples per day collected, the proposed approach is able to provide more accurate estimates of the maximum concentration than the fixed frequency and the random strategies. Even if this tool is appropriate for situations in which the concentration dynamics are stationary over the day, for instance, the time corresponding to the high-low concentration is the same over time, in real-world situations they change over time due to the changes in the water system user behavior and other exogenous factors. In such a situation, one needs to introduce new mechanisms in the sampling strategy that take into account only the data corresponding to the current status of the system. Otherwise, the automatic approach would decide on the basis of data not reflecting the current situation. Two main approaches are commonly used to deal with non-stationarities of the environment. Passive approaches, which use only the most recent data to build models of the process, and active ones, which proactively detect if a change occurred and discards the information before this has occurred. Using the SEC-GP-UCB-CD and the SEC-GP-UCB-SW algorithm, which has been specifically crafted for the sequential monitoring problem, we outperform classical schemes for monitoring, like the constant sampling over time and the choice of random time point over the day. In the figure, we show the points corresponding to the error on the x-axis and the number of samples on the y-axis of the different methods. In this experiment, the two traditional sampling methods, in blue and green, are providing less accurate estimates even using a larger number of samples than the two map-based ones in red and orange. Even in this case, the two approaches are showing that they are more efficient in terms of sample and accuracy in the concentration estimation than traditional sampling approaches. In conclusion, we show how machine learning techniques can be applied to the environmental monitoring field to create smart sampling approaches. These techniques are able to provide a more reliable estimate of the water quality than traditional sampling methods, while at the same time having significant saving in terms of chemicals and time for processing samples. This is far from being the only application of such technique in this field. Indeed, this represents the first synergy between the two fields, which seems to provide promising outcomes in the next few years.